the shift operation. Suppose you have this, and then you do this. You bump this by the amount of what? Alpha t. What's that do in the S space? What do you think? Well, just a lot of these problems are solved by appealing to the definition. So I would have the integral from 0 to infinity, e to the minus s to e to the plus alpha t f of t dt. That would be this thing, right?
S minus t?
Not so fast, Mr. Bond. Okay, let's rewrite this. 0 to infinity, and then we would have e to the minus s minus alpha t f of t dt. So would we not get, I guess this is what you're saying, Dave.
Yeah.
Okay, so that's the translation or shifting property. I'll post all this, give you a gigantic table. Here's another view. Suppose this is true again. So we always start out this being true, but suppose you have a new function. The function g of t is defined to be f of t minus alpha if t is greater than alpha, and 0 if t is less than or equal. What is that? Well, this is just a step over of the limits of integration.
Or not.
Well, let's plunk this into the definition. This would be the integral from 0 to infinity. F of t minus alpha d t minus alpha, right? Alpha is a constant, so that's the same as dt. And now can we do a transformation of variables?
Do we have to split the integral from 0 to alpha and alpha infinity?
Well, I'm going to split it, but I'm going to actually eliminate the part from 0 to alpha right now with this substitution. So when t is 0, let's see, when t is 0, I'm doing this here.
Don't you have to insert e to the minus st?
Well, yes, I do. That's what I forgot. So when t is 0, u is minus alpha, right? And then when t is infinite, u is 0. And then I have t is u plus alpha. So e to the minus st is e to the minus s times u plus alpha. F of u. Okay, I think I'm back on track. This thing, I can pull out e to the minus s alpha. front. And then I have e to the minus su f of u. Now, u is t minus alpha. So if t is greater than alpha, that is to say u is greater than 0, the function is defined. Otherwise it's 0, right? So if u is greater than 0, t is greater than alpha, and we have this. If u is less than 0, we have 0. So I can immediately clip off the piece from minus alpha to 0 because the function is 0 there.
Right.
What's that one? E to the what?
E to the minus e equals e to the minus, let me turn it around, make it alpha s. And now I'm writing 0 to infinity instead of minus alpha to infinity because the function between minus alpha and 0 is 0. So that's the Laplace transform of f, right? So it's e to the minus alpha s f of s. So if I have this situation where the function g of t is 0 up to some point on the x-axis and then starts doing its thing, I can multiply by e to the minus the point at which it stops being 0 times s times the transform of the whole thing. So that's called the second translation of Schiffer's problem. Okay. So I'm trying to pick up all of
What's
it.
the name of that again?
The second translation. Now,
All of this is in the.
it's in just about any book on differential equations of any seriousness.
I bet you can do a browse on Google of Laplace transforms.
Oh yeah, the one I'm going to give you, I think, is a huge table published. You know, just look up Wikipedia, Laplace transform. You get a gigantic table.
No, I was thinking of the book we have at home for Rennie, I forgot.
Arkin and Weber.
Yeah.
It's tremendous. It's back in the bag somewhere. It's covered in detail. I'm using a little bit more elementary book here that just lays out what all these things are, and then once we get a table, we can start playing around solving equations. Well, so far we haven't taken derivative of anything, but let's do that.